most of my talk would be on the numerical algorithm behind web simulation. And at the end of the talk, we'll touch a little bit on the HPC aspect of this work. So we start from taking a look at the elastic web equation, 3D. We're not taking a look at the detail. Some of you are smiling. The only thing to note here is that there are these parameters lambda and mu, which are related with web speed. And web speed enters the equation through these parameters. And this web speed pretty much determines how the choice of discretization parameters are made. For example, if you have a fixed frequency, then the minimum wavelength supported by the medium is pretty much determined by the minimum wavelength. And the delta x, the spatial discretization size, is usually determined by prescribing a fixed number per wavelength based on the minimum. So delta x is proportional to the minimum wavelength in the web speed. And additionally, we also have to determine what is delta t. And in this case, I would claim that accuracy is usually not that much a concern. Most of the factor actually come from the stability condition, the CFL condition. One way to read the last equation on the bottom is that 1 over f basically gives you the period. So that's over what time the web repeats itself. You have the same number of points per wavelength there. If you don't have the factor at the end, that basically means that you're using the same number in space and time for discretization. But because of the additional penalty factor coming from the stability condition there, you're oversampling in time. And this oversampling factor is basically the contrast between the maximum and minimum web speed. So that's why I claim that usually it's not that big a concern for accuracy reason, but mostly delta t is determined by the stability condition. So this is a figure that I have cited quite a few times. It's from a very old book, but it's a little bit unsettling that it's a personal correspondence, but this is where I get my information from. If some of you have better sources, please let me know. The thing to notice here is that there's a wide variety of material in Earth. For example, when you have unconsolidated material like soil and dry sands, the shear wave speed can be as low as 100, where in the consolidated hard rocks, it could be as high as 6,000. That means 60 times contrast in wave speed if you want to incorporate all of those in your elastic web simulation. If you go back to the equation shown in the previous slide, that basically means that you're oversampling 60 times in time because of this contrast. And additionally, in the hard rock region where you have the high web speed, you're also oversampling 60 times in space per direction. But Amdahl's law would kick in the spatial discretization. So I would claim that if you're going to elastic web simulation and you want to incorporate all this variety of ranges of web speed, it's probably not so desirable to run it on a uniform grid. Instead, this kind of non-uniform grid might be more suitable, I would say. But I want to give you a caution that if you're not careful with things, you could have instability issue coming from the interfaces. So I sometimes call this long-term instability because it does not show up at the beginning of the simulation, but it blows up eventually. In case you're not convinced, this instability is actually exponential growth. This is a figure that demonstrates that. I like this figure a lot, so I'm going to spend a little bit of time explaining it. The y-axis is the logarithmic scale, and the blue dots are actual amplitude of the solution at every time step that you actually calculated them. The red one is a reference line coming from its slope corresponding to our eigenvalue. The eigenvalue is coming from the I would say, the propagation matrix. You do your spatial and temporal discretization. You have your solution at one time step. You have your solution at the previous time step. They're linked together by a propagation matrix. And now we have a purely algebraic problem. You take that propagation matrix, you do an eigenvalue decomposition. That eigenvalue essentially tells you is a corresponding eigenvector is going to increase in amplitude, decrease in amplitude, or stay the same as you progress forward. So we took the propagation matrix. The red line is from the eigenvalue with the largest magnitude. It's just a little bit over 1, but that's enough to cause the eventual blow up. So I think this is a very nice, when I saw the picture, I know that we're barking at the right tree. So you have this potential problem. Now the question is, what can you do about that? I like this approach. I like to prevent this from happening. So the idea is that you define a energy estimate, I would call. It's essentially a norm or measure of the amplitude of the solution. I want to emphasize here that this quantity is time dependent. So, okay, we're eventually going to go to 3D, but for illustration and explanation, I think it suffices to take a look at a 1D wave equation. This is a purely continuous case. We have a definition of the energy, kinetic part, and potential part. You take a differentiation with respect to time. You do some calculus maneuver. Eventually, you end up with a term that is on the boundary only. And this is just an observation so far. And another thing that if you have the proper boundary condition, then, for example, sigma equal to 0, then your energy is conserved. So this is the property we want to preserve in the numerical discretization. So here I'm writing out the discretized system almost as a term-by-term correspondence to the continuous case. I have energy that is defined very similar to the continuous case, except that I'm replacing the integral operator with a norm matrix that essentially defines my energy estimate. You do the same maneuver. You take the differentiation with respect to time. You end up with this thing. So it's not obvious that this can be reduced to boundary only, but this is the name of the game. We wanted to design these operators, A operator and a D operator, so that this quantity would reduce to boundary only. And in doing so, discrete energy mimics the continuous energy, so we would have a chance. I'm not going to go to the detail about how you come up with this kind of operator, just assure you that you can actually come up with this kind of operator. If you notice that in the interior, it's actually just the standard operator. You only need to do some adaptation near the boundary. This is the norm matrices. In the interior, it's pretty much just the identity. Only need to do some adaptation near the boundary. And with that choice, which, by the way, is by no means unique. There are many, many solutions up there. You can reduce everything to the boundary. Here, this operator, I would call it a projection operator, is a little bit more complicated than the column vector. This is because we're using staggered grid. So your solution variable is actually not on the boundary. You have to project it over there. If you're not using staggered grid, things can be a little bit simpler. Okay, that was just one part of the story. We managed to make the discrete energy mimic the continuous energy, but we haven't talked about energy conservation yet, and we haven't talking about the imposing boundary condition yet. This is the second part of the method, which is that you impose the boundary condition through a penalty term, and you need to carefully design the penalty term so that when you do the energy analysis, the actual term introduced by this penalty term would exactly cancel out those that are left over previously. So in doing so, you're imposing the boundary condition, and you also preserve the energy conserving property. And by doing so, if your energy as a measure of the solution cannot be allowed to increase, then you cannot have the instability. So that's how you avoid those kind of instability, prevent it from even happening. So that's now that's a 1D demonstration. A few questions can be asked. The first is that can you handle heterogeneous case? I didn't talk about the parameters there. The answer is yes, and it's almost automatic. The physical parameters get absorbed by the definition of the energy, your operators, and also your boundary terms. Almost do not need to be changed. So this one is almost automatic. The second question is, can you handle multiple subdomains? So this is actually where we want to use it. We want to use it to cover different subdomains together so that we can do a non-uniform discretization. The answer is yes. So if you remember previously, we are essentially having a two-step process of the discretization. You do the discretization in the interior of the domain, and then you impose the boundary conditions through the penalty term. So when you have multiple subdomains, instead of boundary condition, you impose the interface condition through the penalty terms here. If you do things this way, the energy would be conserved through the across the interface. So a final question that I put here is that what about beyond 1D? So this is essentially what we care. You can also do this extension, but you need to be careful with the interpolation operator. The interpolation operator go in the two directions. They need to satisfy a certain type of relationship. It's not arbitrary. I'll give you one example here. So here's one very common case. You have a 1-to-2 grid ratio. This operator from red to blue, it's hard to make a different choice. I think this is very automatic to do. But you have to be very careful when you go from blue to red. It's very tempting to just take the value, but that would not be the right thing to do. You have to do an average based on the choice of this operator here. So I'll give you a few numerical examples. First one, both of the numerical examples are in 3D. First one is a layered medium. We have 1-to-2, 2-to-3, and 1-to-3 grid ratio. Number of points per wavelength is kept at 12. And I have a number here, I call it the theoretical 7. So this is, you take the total number of discretization points in both space and time for non-uniform case and uniform case. The ratio is what I would say the theoretical 7 that you could achieve. But before we get there, we first need to take a look at the solution. I think it matches pretty well because the deeper part of the medium are oversampled anyway in the uniform case. So you can get away with using less grid points per wavelength there. And also the energy is pretty much conserved. It's pretty much flat. This is and this is a snapshot. And so this is the HPC part, I guess. So we achieve the empirically collected result. We are 18.7 in terms of the computational 7, just a little bit over 2% of the overhead. We use less number of cores because we have less spatial grid points. And we also use less wartime because they were able to use larger time step. A second example is the overthrust model. So I want to say that this model is not particularly good for this demonstration. So for this kind of discretization, what you want is clearly distinguishable layers. This model is actually not, but we have to do what we got. If you have a better model that it's open to share, I'll be very happy to try it out. The problem is here that the maximum wave speed are pretty much the same across all layers. So we couldn't, the theoretical 7, we couldn't achieve that much. It's very meager. It's just a little bit over 3. But for demonstration purposes, I think it's sufficient. This is the comparison of the signal. And this is the energy. And this is what we were able to achieve numerically. I think it's about a 3% overhead comparing with what is predicted theoretically. And there's a final plot, final table, which is a weak scaling result. I think one of the speakers mentioned yesterday that for this kind of problem, weak scaling is not that hard, I'll be honest. If you don't have it, then something is wrong. So not surprisingly, we have it, and we were able to scale it up to 100,000 cores. One thing that did get me a little bit concerned for a while was that if you observe the trend and you increase the number of cores, the elapsed time actually reduces. I was surprised by that. I have some tentative explanation, but I don't have concrete evidence. And it's really hard to try to figure out what's really going on at this scale. If some of you happen to have some similar experience or observation, I would be happy to know. With that, thank you.
Okay, any questions for Longfei?
Okay.
Yeah.
Thank you for your talk, very interesting. Just what is the order of accuracy in the domain space?
It's fourth order, but when you get near to the boundary, it would have to reduce to, it reduces to second order. So you have a second order coming from a lower dimension. So
And regarding the energy dissipation, what do you do for the absorbing boundary condition? PM?
we didn't put any.
Sorry?
We didn't put any.
If you do, so you have nothing, because you normally have some dissipation of energy. How do you control that when on the different grid sizes?
Yes. You won't be able to have energy conserving property, but I would say this would be the next step. So first, we want to make sure that this works without the absorbing boundary condition. And once you put it there, I think the interpolation operator would be tricky to get. But we would have to look into that.
Okay, yes.
Hey, thanks for a very nice talk. One of the questions I had, I think it is intriguing to see your oversampling of time step.
Okay.
Right. So in a full elastic system, let's not complicate with anisotropy, but let's say a full elastic system, it will really depend on the geological model, right? Sand shell. It will be a completely different than going through like salt and then sediments or carbonates. So have you run any test where you have certain periodic sequences versus big blocks, and then you're jumping from one, changing that time step from oversampling to the optimal sampling? Can you give us some insight in that? Like, how would you choose? I mean, would it be dependent on the thickness of the beds, how it is sequencing, or it will depend on the lowest common denominator, which will be the shear waves, like, or the shear speed?
I think it's mostly would mostly depend on the contrast in the medium that you want to include. If you have a wider range of the medium that you want to include, from let's say high-speed rock to very low-speed material, then you would have the oversampling there a lot.
Yeah, but it's a significant computational savings.
It's very significant. I would say you probably get more out of the time, reducing the oversampling in time, than from the space. Yes.
Okay, let's thank Longfei one more time.